corollary 753, that means the ratio test. Now we have already seen the statement in the previous analysis video, but because we are going to prove it today, let's just quickly repeat the statement. We will be somewhat brief. We won't write everything, we'll just write what it means, what it has. So this is the ratio test because of the presence of those ratios. You already know. So what we are given here is again, of course, a series of real numbers where each term is non-zero. Now there are parts, of course. If this quantity limit superior of the sequence whose general term looks like this, that means its upper limit. If this upper limit is less than 1, then our series is absolutely convergent. Absolutely convergent. Let me write in short like this. And hence it's of course also conditionally convergent, which just simply means that it is convergent. Then part B, on the other hand, if the limit inferior, the lower limit of this same sequence is greater than 1, then our series is conditionally divergent, which just simply means that it is divergent, and hence it cannot be absolutely convergent. And here, because it is absolutely convergent, it is automatically also convergent or conditionally convergent. But here, so that means here we have convergence, here we have divergence. And there is a part C also. In the other cases, we cannot assert any conclusion. That means if you have any other case, then the test becomes inconclusive. You cannot say anything. So let's now see the proof. Since an is not equal to 0 for, we have to mention that also, for all indices, for all n greater than or equal to m, the sequence whose general term is the absolute value of an is a sequence of positive real numbers. That's because we know that any absolute value is a non-negative real number, and an absolute value becomes 0 precisely when the number inside is 0. So non-zeroness of all these an's implies that all of these terms in this sequence are going to be positive real numbers. Okay. Now, because we now have a sequence of positive real numbers, we can now apply the lemma that comes before the ratio test. That is our fundamental lemma which we proved in the previous video. what is its number? 752. Naturally, because this one is 753. So by lemma 752, we have these inequalities. You recall that in the original statement of this lemma, there of course also we have a sequence of positive real numbers, and that was Cn. And here in place of Cn we have absolute value of An. So the corresponding inequalities in this case will be this. Limit inferior of absolute value of An plus 1 divided by the absolute value of An is less than or equal to the limit inferior of the nth root. Oh, here also we will encounter that problem, that if we start things with m, then there may be a problem in considering nth root, especially when m is negative, and hence at one stage we will have to consider zeroth root, which is meaningless. So here also, okay, to avoid unnecessary complexity, let me just change it to 1, okay, which really does not affect anything. If you are thinking how and why does it not affect anything? If you are given a series where, say, your index starts from a negative integer, you can always tweak things, you can change things in such a way that you can turn it into a series where the index starts from a positive integer. If you don't get how, you just think about it. If you don't get it, please let me know, I will tell you. It's not something extremely difficult, it's just it is just re-labeling things, that's all. You can make any infinite series start with a positive index, I mean a positive value of the index. So this slight modification does not change anything. But it will now save us here, because now here we can freely choose n to be any positive integer. And the inequality, of course, the chain continues. This thing is less than or equal to the limit superior of this, which in turn is less than or equal to the limit superior of these quantities, these ratios. Okay, so this is something we are getting from lemma 752. Now let us take the parts separately. If limit superior of these ratios is less than 1, that means if this term is, this quantity is less than 1, then of course this one is also less than 1, then this thing is also less than 1. Now if this is less than 1, then we can apply the root test. Yeah, so by the root test, under this condition, the root test says that our series is absolutely convergent. I don't know why I am stammering today. So by the root test, this is absolutely convergent and hence also conditionally convergent. Maybe there is a system error here, that's why I'm stammering, who knows. And hence conditionally convergent. So that is just part A. Then part B. In part B, if limit inferior of these ratios is greater than 1, then we have already seen that the limit inferior of that other quantity, which is the nth root of the absolute value of an, that is greater than or equal to this lower limit. So that would also be greater than 1. That means this is okay. Shall we write this, or because we don't really want limit inferior itself, but rather limit superior. We know that this is greater than or equal to its own limit inferior, and this is greater than or equal to this, so this one is also greater than 1, and as a result this one is greater than 1. But then again we can apply the root test. So by the root test, this is conditionally divergent, and so I need ink, I think, and so cannot be absolutely convergent. And as far as part C is concerned, namely the other cases where the test becomes inconclusive, that we will handle in the exercises, because we have to also see the similar thing for the root test itself. We left it hanging, so we will deal with that in the exercises. And in fact, let's just write that here itself and complete the proof in this incomplete manner. We deal with part C in the exercises. So that is the proof of the ratio test. Now after this, there is another application of that lemma which we saw in the previous video. That means the one which gives us those inequalities involving upper limits and lower limits, and this is this next proposition. So you can see, before we go to the proposition, you can see one thing, that in the proof of the ratio test, we needed not only that lemma but the root test itself. Without the root test, we cannot say anything about the ratio test. I mean, we cannot prove it. And this proposition is just simply a limit. That is, if we consider the sequence whose terms go like this: 1, then square root of 2, then cube root of 3, then fourth root of 4, fifth root of 5, just like that, and then that sequence is convergent and its limit is 1. If you think about the sequence just like how the sequence is given, it's a little difficult to decide whether it is convergent or, I mean, what the limit is. Just from the look of it, it becomes somewhat difficult to decide, because you have the variable n here as a base as well as in the exponent. But using our lemma involving those upper and lower limits, we can in fact actually say that the limit is 1. Okay, since the sequence of all positive integers, that is our ordinary sequence of all non-zero natural numbers, this is a sequence of positive real numbers. We have by lemma 753 these inequalities. So the sequence Cn that we have in the original statement of this lemma, now in its place we have the sequence of all positive integers. limit inferior of those ratios. So what will they be? The general term will look like this: is less than or equal to the limit inferior of the nth root of n, which is less than or equal to the limit superior of the nth root of n, which in turn is less than or equal to the limit superior of these ratios. Now the nice thing here in these inequalities is that these two things actually are the same, they are equal, and it's a real number. Note that in fact the sequence whose nth term is n plus 1 divided by n, where n is a positive integer, is convergent, and from the limit laws we know that its limit is actually equal to 1. So from the basic properties of upper limits and lower limits, we know that when we have a convergent sequence of real numbers, then its upper limit as well as lower limit both are equal to its limit, and that's what we have here. Here n plus 1 divided by n is a convergent sequence of real numbers and its limit is 1. So this will be 1 and this will also be 1, but I can't recall again the number of that result, which it is coming from the chapter on sequences and their convergence, but you understand what I am talking about. So I will just simply write like this. So by the basic properties of upper and lower limits of sequences of real numbers. You understand that we need not write this much. We can just simply refer to that lemma, theorem, whatever it is, and its number. But because we don't remember that and I don't have it here, I forgot to write, so I am writing like this. The upper limit is 1 and the lower limit is also 1. But these upper limit and lower limit actually trap the upper limit and lower limit of the sequence n to the power 1 by n in between them, so they also have to be equal to 1. This is equal to the lower limit of these ratios. Hence this is also equal to 1 and that is equal to the limit superior, that is the upper limit of the nth root of n. So again, by such basic properties of upper and lower limits, now by one of those properties we can say that the sequence n to the power 1 by n itself is convergent and its limit is 1. So again, by the properties of upper and lower limits, the sequence n to the power 1 by n is convergent and its limit is 1. When you write this statement, that is, the limit of a sequence is something, a real number, then the fact that it is convergent is included in that equation itself. Okay, so that is the proof of this proposition. And now the section is going to end, but before it ends there is a remark. So in this section we have seen the two very useful tests for absolute convergence, the root test and the ratio test. Although their true usefulness actually has not been seen. Okay, we have not shown whether they are really useful, because so far we have been working with the theory. In the exercises that come next, which we of course we will not deal with in this video, but in the next video, there we will see that yes, we can in fact say a lot about convergence of series using these two tests alone. But still there are other tests, and one of the other tests we are now going to mention in this remark. So that gives us 3 tests, but there are others also which you may already probably know. So the third test that we are going to see, not now but much later when we deal with integration, it is known as the integral test. Besides these 3 tests, there are others, of course. Gauss's test, Rabi's test, and there are others also. I don't remember their names, or for that matter the tests, I mean the statements of the tests. In addition, to the very useful root test and ratio test for convergence of series, we shall see another convergence test, called the integral test. Which we will cover in proposition 11.6.4. We are still far away from that, but we will eventually get to that. Proposition. And with this section ends, minus the exercises of course, which we will start solving in the next analysis video, that means coming Sunday. So that's it for tonight. If you want to say something about these things, you can use the comment section below, or you can mail me at my usual address. The link will be there in the description. And this tomorrow we don't have any upload. Day after tomorrow, that is on Tuesday, we are again going to see number theory, where I think we are currently solving problems on greatest common divisors, and in fact not just simply greatest common divisors, but the Euclidean algorithm. So that being said, this is just it for tonight. So see you day after tomorrow with number theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.